Exponential functions are commonly used in areas of business and mathematics. To find their derivatives, we're going to need to start out from the definition of the derivative and then set f of x equal to e of x in that definition. So what that means is we're going to have to take the limit as h approaches 0 of f of x plus h minus f of x all divided by h. I'm going to go ahead and in place of f of x plus h, I'm going to put e to the x plus h, and in place of f of x, I'll put e to the x. And now I need to take that and try and simplify it. The reason for that is if I try and put h equal to 0 in here, what I'm going to get is 0 over 0, and that tells me that I need to do some simplifying. When I look at this expression on top, I can rewrite it a little bit to let me do some of that simplifying. Let me take e to the x from each one of these terms. So I'm going to write the e to the x out in front. And to figure out what goes inside, remember that e to the x times e to the h, when you multiply things with the same base, you add the exponents. That's what gives us the x plus h. And e to the x times 1 gives us e to the x. E to the x doesn't have h in it, so it has nothing to do with the limit as h approaches 0, so we can go ahead and we can move this out in front. What that leaves me is e to the x times the limit as h approaches 0 of e to the h minus 1, and in the bottom, h. To do this limit, I'm going to have to go ahead and make up a table like I've done in some of the past sections. So I've gone ahead and put a table here with h values that get closer and closer to 0 because that's what we're doing in our limit. And now I'm going to plug in these numbers in place of h and see what I get. If I put 0.1 into e to the h minus 1 over h, I get about 1.0517. If I put in 0.01, I get 1.005. I get an extra 0 in here. If I put in 0.001, I get 1.0005. And if I put in 0.0001, I get 1.0001. What you'll notice is as h gets closer to 0, this quotient gets closer and closer to 1. The value of my limit based on this table is equal to 1. So I go ahead and put that in. E to the x times 1 gives me e to the x. Based on the definition of the derivative of e to the x is e to the x. It gives me back exactly the same thing. Here I've gone ahead and written that out. The derivative of e to the x is simply e to the x. Now let's be a little bit more general about this. To find the derivative of exponential functions with a base of a, we'll rewrite a to the x as e raised to the ln of a times x. Now, that may look a little bit strange, but it's really not that complicated. If you take a to the x, let's think of the a here as e to the ln of a. Remember, when you put a logarithm inside of an exponential function with the same base, they cancel each other out, so this would just be simply a. If I go ahead now, because I have a power raised to a power here, I can multiply these powers. I end up getting e to the ln of a times x. So in order for us to take the derivative of a to the x, I'm going to instead take the derivative of e to the ln of a of x. The reason for doing that is we already know what the derivative of e to the x is. This is simply a composition of e to the x and ln of a times x. So let's go ahead and use the chain rule, with g, the inside function, being ln of a times x, and f of x, the outside function, being e to the x. Notice that if I go ahead and I put ln of a times x in place of x, it gives me the function that I'm trying to take the derivative of. That tells me that the chain rule is an appropriate thing to use here. The derivatives of g and f, well, the derivative of g, ln of a is just some number, so the derivative of a number times x is just that number, so ln of a. The derivative of f, like we just saw, is just e to the x. So now I'm going to go ahead and use the chain rule to write out our derivative. Remember, the chain rule says that I take f prime and I place g of x into f prime, and then I multiply it by g prime. Here I have f prime. I've placed g into it. That's why I have e to the ln of a times x. And then I'm multiplying that times g prime. So this is my f prime g of x part. And next to it, I have my g prime part. My final answer here, because remember e to the ln of a times x is simply a to the x, as we had up here, is ln of a times a to the x. So it's a lot like when we did an exponential function with a base e, but here when we take the derivative we get this extra piece, ln of a. And notice that if a was equal to e, we'd have ln of e out in front, and ln of e is 1, so we just get e to the x, so it makes sense. Our derivative of a to the x is ln of a times a to the x.